Welcome back to Dry Bones, where you don't have to leave your head or your faith at the door. So today we're going to be talking about the dating game, right? Not going out on a date, as many have thought that I was talking about when I told them I was doing this podcast, but the dating game of the earth. Is it too old? Is it too young? But we're going to talk about not how old it is or how young it is, but the methods that are used to date the earth, and then some limitations and some problems with some of those methods, different arguments for those methods. So just like old earth view and evolution say that the earth is about 4.6 billion years ago, young earth view says that it's about 6,000 years old, and that's a huge difference, right? Yeah, so how we determine the age of the earth and how old the fossils are that we find in the Earth's layers affects these viewpoints and the arguments between them. So today we're going to look at several dating methods used as what their ability and limitations are. So my name is Kathleen. I have a master's in anthropology with an emphasis on archaeology. Also, just to let you know up front, my bias is that I am a Christian. If you were to put me in a box, you might say that I'm an old Earth creationist. But I'm also an evolutionist. And so I just kind of want you to know that bias up front as we kind of go through these discussions. I do enjoy taking a look at those issues that help Christians understand that you can be a scientist and a Christian. And that's what a large part of this podcast is about. But also I plan to do some more, some like kind of fun. Well, I find that fun, but also some fun stuff, looking at some other types of things, just really anything that I find really interesting. But I do like to say that I want this to be a conversation, not a debate. So we're going to be discussing a lot of geological principles and methods today that are involving both relative dating and absolute dating. And so, as I said, I'm an archaeologist. I'm not a geologist. So we're only going to be touching on the basics of these methods. I really feel like this podcast actually took me a really long time to work on because I did have to learn so much that was outside of my normal realm. Obviously, as an archaeologist, I'm somewhat familiar with a lot of the dating methods, but I really wanted to give you guys a little bit more grounding in those dating methods because I know that this is a really big crux of a lot of the discussion between whether the Earth is 4.6 billion years old or 6,000 years old. But I also understand my own limitations by not being a geologist. Now, in the future, I do have a friend who's a geologist who I would really love to bring on, and hopefully that will happen. I actually really love to discuss like the Grand Canyon with him and go really in deeper detail as well as these methods. Maybe it'll be a couple of different podcasts if he's good with that. My dad was a geologist. Unfortunately, he did pass away when I was 23. So otherwise, for sure, I would have him up on here. And that would be really exciting to be able to discuss this with him. And he was a petroleum geologist, so even more so, he was obviously dealing with things that decayed, depending upon your point of view, a really, really long time ago. I am going to put his picture up. This is probably not going to be my only time to put his picture up. I'm not going to lie. Maybe a side note is I'm hoping that somebody who worked with him a long time ago might somehow stumble across this podcast and get in touch with me. If you're out there, you knew my dad, please leave me a comment, and I would love to get in touch with you. But moving on. So like my videos about the different types of creationists and discussing about scientific bias, this video is meant to give a foundational understanding as well as it be a reference point for future topics, because I know that in future topics, scientific methods for dating are going to come up. And so I'll probably refer back to this one when that happens, as well as bias, because bias and dating methods come up often when discussing many controversial archaeological topics. So let's start out with what I have heard just in some of my research, plus talking with other people, talking with both evolutionists and young Earth. What are some, and then just in the research, what are some of the issues that I've heard come up? So what I'm going to do is I'm going to tell you what these issues / questions are. Then we're going to talk about all the different dating methods. And then we're going to come back to these questions with maybe a little bit different understanding of how they might be resolved or not resolved or whatever. But that's sort of how I plan to do this. So questions, dating methods, then coming back to those questions. All right. So one of the things that seems to come up often as an argument is this principle of uniformitarianism. And at the end, I'll explain that principle a little bit more. But, just how do we know that things weren't different during the last several thousands, millions, billions of years that could have sped up some of these patterns that we're going to talk about? Another issue that I've heard about is this aging of the rock at Mt St Helens. So there tends to be these outlandish dates of these rocks that come up when we actually did see that erupt and know when it erupted. And then there's this question about what does it mean when these rocks were reset? Third is how do we know the full life of an element in order to figure out what that half-life is? Fourth, how do we find carbon in fossils older than 50K when, as we will talk about in a little bit, carbon-14 dating only goes back about 50,000 years? Then another issue, number 5, is the heat problem that comes up often when talking about young Earth solutions to some of these dating issues. So number 6 is, do scientists date only with methods based on preconceptions of assumed dates? And number 8, what about these trees that they find standing up through several layers of the Earth? How does that happen? What does it mean? Does it mean young Earth? Does it mean old Earth? We'll discuss that. And then what about plains that were found under many, many layers of ice, but we know them to only be 50 years old, but yet ice layers, as we'll talk about, are used to date time. So yeah, lots of questions, and honestly, that only touches on them. There were several more, but like I said, this really took me a long time to work on this one and get this one prepared with the research. And I actually ended up deleting several because I was like, I'll do that later. Okay, so now let's move on to where I talked about, we're going to talk about relative dating. We're going to talk about absolute dating. And then, like I said, we'll come back to these questions. But pay attention as we go through them with those questions and see if you can kind of figure some of that out. So, relative dating, what is that? So this is the dating of sites or artifacts based on their relative relationship to each other in the rock layers. And so it's based on the stratigraphy of these rock layers. And this was where the law of superposition comes in. So where it shows the deeper layers are older and the layers above that are younger. So if you can think of a stack of pancakes, the bottom ones, we're going to, the ones in the bottom of the stack were made first, so they're older. The ones on the top were made last, so they're younger. And so by looking at how layers sit on top of one another, scientists can determine which fossils that are in those layers are older or younger. And then part of this stratigraphy, also we have the law of original horizontality. And so this means that the layers were laid down horizontally originally, and then later they got curved and bent up and sideways and all that kind of stuff. And then part of this relative dating too is something that we call index fossils. And these index fossils are species that lived during very short and well-defined periods. And they were widespread. So they're found worldwide. And what this allows is it allows the rocks to be correlated across regions. And these fossils will kind of act like almost like a bookmark in the geologic record. So if you find the same fossil in two different places, you know those rocks are about the same age. Now, some of the issues with relative dating is things like bioturbation. And bioturbation is when like animals, little rodents or whatever, are going to burrow through these different layers. So then they're going to, move as they burrow. Those rocks and dirt and everything is going to move, or burrowing up. It's gonna make some mess of that. Then flooding is going to cause some issues. What makes me think of this is, so right now we are, when I'm recording this, we are in August of 2025, and July 4th of 2025, there was some horribly catastrophic flooding in Texas. I happened to be in Austin that day and driving through that rain that happened. And if you watched any of those videos, you can see how much that flooding really dispersed lots and lots of dirt. And so you can imagine that's also going to, depending upon the immensity of flooding, how much that can mix those layers together. And then we have earthquakes that are going to shift those layers and move them around, and do things like that. That's going to kind of cause some issues. And but typically we can tell when those things happen as we look at the layers, or not we, because I'm an archaeologist, but geologists can tell. So I should say researchers and scientists can be recognized in the layers, and they can kind of account for that, because they'll see, like if you're burrowing. So as an archaeologist, we might see a post hole. So where we know where we see this area in the layers we deal with, we deal with much shorter layers than geologists do. And you'll see where that post hole has gone in. So in the same way that we can visually, or that we can determine that and recognize that, they are also able to recognize these different situations that might have happened. So in written history as well, we will have documentation for some of these catastrophes. And that also helps date those layers when we do see those results, like particularly like if we know that a volcano erupted and we know how far that ash goes, and we see this layer of ash, then we'll know, we can kind of time that out. The result is that this establishes this geologic time scale. It's a relative order, but we don't have exact years except for things like when there is something in written history or whatever. So, but the years can be established if the layer above and the layer below get dated. So now we're going to move into absolute dating. It's also called chronometric dating. And this is when we actually do put a date or age on a site, on an artifact, on a layer, etc. So if we can date one layer with absolute dating, then using relative dating, we can know that the layers below are older, layers above are younger than that layer. So radiometric dating is a major part of absolute dating. And this was discovered in the 20th century. And by the name, probably it doesn't surprise you that it involves radioactivity. And what's good about this is sort of like what we talked about, by putting these absolute numbers on these geologic timescale, and then it helps us with relative dating. So when radiometric dating first emerged, scientists were skeptical, but as they tested more rocks from different places, the results would line up really nicely with the relative ages that they had already kind of basically established by stratigraphy. So it was like putting two puzzle pieces that just kind of like we're snapping together. So it works through utilizing unstable isotopes that will decay into stable isotopes. And then by looking at that, we can determine their half-lives. So different isotopes have shorter and longer half-lives. And so the half-life is that time that it takes for half of the parent, the original isotope, to decay into a daughter isotope. So by counting how many parent and daughter isotopes there are, researchers can determine how many parents the isotope started with, how long since it started decaying, and then what that half-life is. So once we know that half-life, then that rate of decay can be determined. And then by knowing that rate, then the age of the tested material can be determined. So as the element makes this change, energy in the form of radiation is released. So keep that in mind for the heat problem from our questions at the beginning. So the best rocks to date for this are igneous. That melting process that happens and the crystallization that happens, it resets that isotopic clock that's going on in these rocks. And so resetting it means that all the daughters are diffused. So all those daughters are diffused out of it, and it brings everything back to the parent only. Now, metamorphic rock is not good because that metamorphism is then what's being dated and not the original formation of it. So, and just keep in mind that there might be some rocks that don't diffuse all their daughters when they're melted, and so those are not used for reliable dating. And then also, again, once there's like no more parent isotope, like everything's turned to daughter, then it's no longer any good to be used for dating anymore. So that's not part of it. So let's talk about these different elements that get used in this type of dating method. Obviously, I don't think anybody has not heard of carbon-14. And so this is probably the most famous, but in a way, it's also the most limited. It is found in organic matter. It gets developed in the atmosphere. So then plants will receive that through photosynthesis. The cows eat the plants, the humans eat the plants or the cow, and then both animals and humans can also breathe it in from that atmosphere. And then you can imagine when they die, they're no longer taking that in. And so that's how that gets dated. So what is carbon-14? Carbon-14 has 6 protons and 8 neutrons, and it is this number that makes it unstable and thus decays. If you were to look at carbon-12, which has 6 protons and 6 neutrons, by having 6 protons, that's what makes it carbon. By the number of neutrons, what gives it its isotopic name. And so carbon-12, 6 protons, 6 neutrons, and carbon-13, which is 6 protons and 7 neutrons. So if you paid attention, that carbon-12, 6 and 6, 12, carbon-13, 6 and 7, 13. So those are both stable and they do not decay. Keep that in mind when we discuss one of those questions brought up at the beginning later. Now, a limitation carbon-14 has is that it decays much faster than the other isotopes, and it only works for those once living or organic materials. It's only reliable for up to about 50,000 years old, and it can be contaminated by surrounding organic matter. All right, now let's move on to potassium-argon and argon-argon dating. Now, I put these two together because basically potassium-argon is just sort of the more reliable method of potassium-argon. So in a way, they kind of work basically the same way. That's why I wanted to just put them together instead of trying to explain them both differently. So this is good for dating volcanic rock and geologic events like volcanoes and earthquakes. When lava is a liquid, the argon is escaping. But when it cools, that argon gets trapped inside. So this can be applied to like volcanic ash found in rock layers and at archaeological sites. And what's happening in this is that the potassium-40 is decaying into argon-40. The benefit of argon-argon versus potassium-argon is that argon-argon can be tested with a much smaller sample. It also allows the same rock to be tested multiple times, which will reduce that error and that problem of contamination. So potassium is an inert gas that gets trapped in the rocks in their crystalline structures. And they measure that with a mass spectrometer. And so this is good for dating volcanic, also known as igneous rocks. And it can be used to date 100,000 to billions of years. Now, its limitations are that it's not accurate for anything under 100,000 years. And that's one of these problems that happens based on some of our earlier questions. We'll come back to that part. It can contain older argon. That's another limitation that didn't completely get removed. You can only do this on igneous rock, not sedimentary rock. And contamination can happen by things such as like later geological processes that may have reheated it and released some of that argon. All right, so another method we're going to talk about is fission track dating. And this is about counting damage trails, and these damage trails are called fission tracks left by splitting uranium atoms. So when uranium atoms in minerals split spontaneously, they leave tiny damage trails that are like scars in the crystal. And by counting these tracks, scientists can estimate the rock's age. So these tracks are created by high energy particles of uranium-238 fission and the release of uranium-235. And this is responsible for 40% of Earth's internal heat. This half-life is 4.5 billion years. And so for our questions we discussed at the beginning, consider if that process, considering that these are high energy particles, they're releasing a lot of energy, they're responsible for a lot of the Earth's internal heat, and consider if that process was sped up to 6,000 years. And so this is also used to date tectonic events and mountain building. So one of its limitations is that it does assume uranium concentration and rate based on current observed maximum rates. Another method, and this is our last radiometric dating one that we're going to talk about, is uranium-lead. So this is best for the oldest rocks and for meteorites that are like for the billions of years. So initially, there's only uranium in the rock. This uranium is slowly decaying into lead over billions of years. So the process it uses is it has a multi-step decay process. So it's not straight from uranium to lead. It also has a 2-chain decay process that makes it really reliable because the process itself, by having these 2-chain decay processes, it's basically a cross-check system. And so one chain is uranium-238 that decays to lead-206, and it has 14 intermediary steps in between. So it's not just uranium to lead like some of the others that we've looked at. It has 14 isotopic steps that it goes through between those two. The second chain process is uranium-235 to lead-207, and that one has 11 intermediary steps in between. So by the time it gets to lead, obviously you can imagine the more lead, the older the rock. And it's unique because lead has a greater mass than potassium. And so in order to create this conversion or to figure out this conversion, that difference in mass has to be taken into account and is part of sort of the mathematical equation they do to figure that out. And so one of its limitations is that you have to assume that there was no lead at the beginning of this. All right, let's move into other methods that are also absolute methods but aren't a part of this radiometric dating. So one is dendrochronology. And I'm smiling because I don't know what it is about dendrochronology, but I find it really fun and interesting. And maybe it's because I did a paper on Southwest America in school, and it talked about dendrochronology, and I don't know why. It has a little soft spot in my heart. That probably makes me weird, but it is what it is. Okay, so one day I will do a video on paleoecology, and this is one of those things that will come up again with in one of these videos, because not only is it for dating, it can also tell us about past environments, because this method will involve counting tree rings. And many of us have known for years that you can tell the age of a tree by counting its rings. But how does that help us date artifacts? Well, when looking at the rings of a tree, a wider ring indicates the tree grew more that year, maybe it was a year with more rain. And then a thinner ring will indicate less growth. So maybe there was a drought or some other kind of environmental issue that allowed that, that just kept that tree from growing too much. So that's what I mean by it can tell us about past environments, right? So those wider and thinner rings create a pattern. And so what they can do is take the ring patterns of a younger tree, compare it to the ring patterns of an older tree, line them up like this. And then a lot of times too, the dendrochronologists are keeping tree samples. So it's not just like, oh, they're going to cut down this tree, check it out, cut down this older tree, check it out. They're keeping tree samples, but you also are going to find like a timber that was used for building a house or something like that. Or maybe there is some petrified wood, or they still find some old wood in a hearth or something that somehow got preserved, right? So by using those, as long as you can see the rings, and these can be compared with other patterns, this will give us at least a minimum date of when that tree was cut down and used. Now, the limitations with dendrochronology is that it can only date to about 10 to 12K, and it can only be used with trees that have this regular annual tree growth. If it's a tree that doesn't have that annual tree growth, they're not going to use that tree for dating. And then so let's move on to another sort of similar method, and this is using ice cores. And so this is similar to dendrochronology, and in a minute we're going to talk about speleothems, but they're not rings, they're layers when we're talking about ice cores. And these can date up to 800,000 years. And honestly, that's just dependent upon how deep the core goes. These layers are created by the changes in temperature when the ice melts and refreezes in these summer, winter, rotating patterns, right? So when it gets frozen, that air gets trapped in the tiny bubbles. And so they can even test the level of the CO2 that was in the atmosphere when that layer froze. They also can find impurities such as ash that can be seen in the layers or trapped in these bubbles. And when they see something like that, that can be compared to a known volcanic eruption or other known events to help correlate the layers. It can also be measured through just that visual stratigraphy of counting the layers. And then they can also measure the stable, heavy isotopes like hydrogen and oxygen, and how that oscillated between the temps of that winter and summer cycles. A limitation with this is that there is ice in glacial flows, and that ice is going to be, in that glacial flow, is going to be altered due to that movement, and it will distort the layers, it will add layers, it will take away layers. And so for this reason, researchers only take cores from the center where the ice flow is not a factor. And so keep that in mind when we discuss some of the questions from the beginning, particularly the airplanes that we talked about. Okay, and then another method of absolute dating is speleothems. Again, this one has a little bit of a soft place with me because my thesis dealt with a cave, and we talked about flowstone and stuff like that. And I was working in paleo environment was my thing as part of that paper. And this too, sort of like dendrochronology and ice cores, they can all be used to look at past environments. Not what we're talking about today, but just an interesting thing. And that will be for a later video. And so this is dating cave features such as stalagmites and stalactites, the flowstone, etc. So It's created by the water seepage from above the cave. So the water comes, on top of the cave, it goes through the earth, and then it seeps through that cave roof, and it drips, and it creates these different things like stalagmites, stalactites, flowstone, etc. And so these are mostly made of calcium carbonate, like calcite or argonite. And now, as it seeps through, it can get mixed with iron oxide, manganese, mud, silt, etc. And again, that rate, those things it gets mixed with, all that kind of stuff, that can also help determine that past climate. You can imagine that as those environments, as less rainy time, more rainy time, that's going to change the rings as it's dripping. Sometimes it's going to drip more, sometimes it's going to drip less. And so that growth is going to indicate those levels of moisture in a year. It also can be dated by uranium series dating. The data from the Speleothems has gone back as far as 289 million years. There is a cave in Lawton, Oklahoma, where they have dated it that far back. One of the limitations with that, cave depositions are going to be at a different rate than outside of the cave. So another method is thermoluminescence dating. So minerals like quartz can trap electrons when they're buried. But if you expose them to light or heat, those electrons are released and they emit like a faint glow. And so measuring that glow tells you when it was last exposed to sunlight or fire. So thermo means heat. Luminescence means light. And so this is really great for like pottery or burnt flint. For instance, you have a ceramic pot, and ceramics have to be put in a kiln and heated up to make them strong. And so it can tell when maybe that happened. Or if that ceramic pot was used for cooking, it will tell us the last time that was used for cooking, or it'll tell us when it was fired. It just basically gives us a minimum age of the last time the humans utilized that piece of that pot, that ceramic pot, or made it, but basically it can give us like that, at least that minimum thing. And then with burnt flint, a lot of times when flint knappers will make their arrowheads, they burn them to help them work with the rock better and stuff like that. So that will also give us a date of that. It is a form of radioactive dating, but it's more about dating the accumulated radioactivity rather than what gets lost. And one of the limitations of this one is because it gets tested by heating it. An artifact can only be tested once, or the sample or whatever. It can only be tested once because otherwise you've kind of restarted it. Okay, another method is, and I'm going to try really hard to pronounce this on the first time, magnetostratigraphy. Magnetostratigraphy. I have tried this so many times, practicing it before I did this. I've not gotten it. I tried to listen to other people say it, could not get it. So I'm going to say its first limitation is pronunciation of its name. Just going to throw that one out there. It probably doesn't get used a lot because nobody wants to talk about it in their report if they have to talk about their report. Okay, but in all seriousness, this is about dating based on the magnetization of a rock. And I find this one really interesting because it's how it lines up with the Earth's polar magnetic field and the polarity of the Earth's magnetic field. So over history, now some of you guys, this is going to be a duh moment. Some of you guys are going to be like, I had no idea that happened. But so over history, Earth's magnetic field has actually flipped many times. And these flips are recorded in volcanic rocks and sediments. The minerals in those will orient themselves in the direction of the Earth's magnetic field, and they'll create a pattern. So if you find a pattern of magnetic reversals in a rock sequence, you can match it against that global record, and it's like matching fingerprints. So here's what happens. So as this switch happens with the magnetic field, the first thing that happens is that intensity of the magnetism will slow down. And the flow of the Earth's electric currents gradually will just reduce to zero. And then that reversal takes place. And so then that intensity gradually returns back to the regular value. So when those two things happen, it creates a pattern, right? So if it's a single if everything's lined up and it's a single polarity, that's one pattern. Or it might be sort of intricating normal and reversed and all this sort of stuff. And that's a different type of pattern. And when we say normal is going to be the north seeking of how the current North Pole is right now. Or it might be dominantly either normal or reversed. And so like there might be some that are reversed, but most of them go normal. So that's another pattern. And just to give you an idea, there have been at least 4 major polarity epochs and several what they call supercrons that have happened and throughout the time of Earth. And the pattern of the rocks can tell the age based on these epochs and supercrons. It's probably pronounced epochs. Epochs or epochs? I don't know. Tell me in the comments how the correct pronunciation of that. And you know what? I'm going to give you guys bonus points if you can record yourself saying magnetostratigraphy. I actually think that's the closest I've gotten to that, pronouncing it right. But yeah, I don't know what those points are going to mean, but I'll give you extra points if you can say that word, record it, and put it in the comments. Can you put a recording in the comments? Well, just do it for fun if you can't. Okay, so the patterns of the rocks can tell the age based on these epochs and supercrons going back to 485 million years ago. So that can also be dated really, really deep time. All right, so we've talked about the different dating methods. How does this mean about dating fossils? Because the fossils are actually rarely dated directly. I mean, sometimes they can. Carbon-14 sometimes can. If it's a living organism, sometimes carbon-14 can work. But remember, that only goes back reliably 50,000 years ago. So common methods for dating fossils involve like dating that volcanic ash or lava layers that may be above or below that where that fossil is, so the fossil-bearing strata. We can date the minerals within the sediments if possible. And then using stratigraphy and index fossils, we can figure out that relative positioning. So what you're really looking at is that fossils are typically aged by how they're bracketed. And so this relative aging. So the fossils are typically dated with the relative dating, but the relative dating is dated by that absolute based on the rocks and stuff that are in it, is pretty much the typical way of doing it. And that's why a lot of times it'll be like they're between this age and this age when you look at a fossil. And that's why they sometimes can't pinpoint those a little bit more exact. So just kind of talking about this, like using these methods, this is what, and I'm going to say old age scientists, so scientists who believe in a 4.6 billion year Earth have determined is that the oldest rocks on Earth were found in Canada and Greenland, and they have dated those to about 4.0 billion years. There's also zircon crystals that were found in Australia that were dated to about 4.4 billion years. And when they find a meteorite and they date a meteorite, those are consistently dated to about 4.54 billion years. And they use that uranium-lead method to do that. So keep this in mind. Again, we're about to get back to those questions. And with these, multiple lines of evidence converge on the same age of these different things. So dating these meteorites at 4.54 billion years, and the fact that they consistently through dating methods give us that because it's not based on just one rock or one technique. It's a very consistent time frame. It's a product of thousands of measurements across multiple methods, and they all point to that same conclusion. So let's get back to those questions, all right? So first, we talked about that principle of uniformitarianism, and this comes into play a lot in a lot of the arguments. So before we go into that, I just want to take a quick second and share a verse with you guys that I do think is going to come up a lot with this principle of uniformitarianism, but also it is going to come up a lot for many of the discussions we're going to have through these different podcasts. So in Jeremiah 33:25, it says, "But this is what the Lord says, I would no more reject my people than I would change my laws that govern night and day, earth and sky." So I believe that from a Christian viewpoint, God is referring to these laws of physics that we see in these dating methods. And I think this verse gives Christians a solid place to land when we look at how the patterns God has in place today, He also had in place in the past. All right, so let's get back to this. So how do we know that things weren't different during the last several thousands of years that could have sped up some of those patterns that we see in these rocks as the decay happens and stuff like that? I guess, honestly, we don't. And this could be where something like punctuated equilibrium, and I do discuss that in my creationist video. I discuss it briefly, and maybe one day we'll discuss that a little bit more in depth. But that is maybe where something like punctuated equilibrium can come into play. But to be honest, I believe those would be exceptions. And because we wouldn't know exactly when that might have happened, or we can guess or whatever, but they are going to be pretty unreliable, or what caused them or whatever. They're going to be mostly unreliable for creating predictions. Kind of think about, like Occam's razor or the principle of parsimony. Like, I think a lot of people know what that is, but just in case you don't, it's a philosophical principle stating that when faced with competing explanations, the simplest one that adequately explains the phenomenon should be preferred. In order to make predictions for the future or studying these past processes, it is necessary to make some assumptions, but this doesn't make them suspect, but just really honestly merely as part of a reasonable explanation. And for instance, I'm going to use an example that might be a little easier to swallow, right? So here is Jonathan the tortoise. He, as of 2025, is estimated to be about 193 years old. So how do we age a tortoise? Because obviously there was no one alive 193 years ago to see it born. So scientists look at factors like shell condition, the size, the metabolic profiles that they will see occurring in younger tortoises to see how they age. Then basically using this law of uniformitarianism, they study those characteristics in Jonathan and make assumptions to calculate how old the tortoise is. It is an assumption. And it's a method utilized in many areas of science that typically are relied upon without question. I imagine when people have heard how old a tortoise is, they're like, oh, wow. And they're just in awe of how old a tortoise is and this sort of stuff. Not a lot of people question, oh man, that's no way that can be right. Something could have happened that all of a sudden that tortoise's life sped up really fast and then it slowed back down. Because we see tortoises today, we see how they grow, we see it's pretty stable or whatever, and we see it faces a certain type of pattern. And so that's exactly what they're doing when they're doing this radiometric dating or the ice cores or, the dendrochronology or the speleothems, or the, fission dating or whatever. They're looking at these patterns that we can see happening today. We can calculate how fast they are happening today and then make the assumption that that's how fast they were operating back before. And that was the processes that were taking place back before. Is it an assumption? Of course. Is it a reasonable assumption? I would say yes. Okay. So another question we had at the beginning was the aging of rock at Mt St Helens. So how is it? This is a thing where it seemed to come up a lot between old Earth creationists and young Earth creationists, where we know when Mt St Helens erupted, and then 10 years after it erupted, they took dates of some of the rocks, and some of those dates that were taken, and I'll be honest, I only saw this from young Earth creationists, came up with some really outlandish dates because they knew when it erupted. And so if you notice on this chart, there are minimum dates that some of these methods can date for, and that's part of their limitations, is that there are minimum dates. Just like there are maximum dates that are a limitation, there are also minimum dates. And so if you use one of these you can't even date something younger than 100,000 years old to date something that's 10 years old, that process of whether it's, a mass spectrometer or whatever, it's not going to know what to do with that. It's not going to know what to do with such a young age. And so you are going to get these bizarre numbers. It's not reliable, and it's not how these scientists are doing it. And that is part of why we'll talk about this in a minute, but that's part of why they sometimes do have to make an assumption and use a particular method that works with that assumption. I mean, think about it. If you were to use like a bathroom scale to measure a truck, well, that scale wouldn't actually be able to measure the truck. I mean, I'm sure each of you guys, in your line of work, if you use the wrong tool, the wrong software program, the wrong piece of equipment in a way it wasn't designed for, you're not going to have good results. And so that's the same idea here. That is also why things are double and triple checked and cross-checked with other methods and that sort of a thing. And so along those same lines, part of that question before was, what does it mean for these rocks to be reset? Because when those rocks were lava and they erupted, they were reset. Okay? So when the rocks melt, that releases all those daughter isotopes. I kind of went over this before, but I'm going to put it back in this context. So then it's only the parent isotopes again. So how do we know the full life of an isotope in order to figure out what that half-life is? And I think this one trips people up, but really it's not all that difficult. It's basically you count all the parents and you count all the daughters, and that's what its full life is. So then if half of that number is daughters and half of it is parent, then that's its half-life. So, or, if a quarter of them are, then, you can just kind of do those calculations. Even if not half of them have turned into daughters yet, you can still do that calculation. And so that's how that works. So why do we find carbon in fossils that are older than 50,000? And does that mean that that method is bunk? Remember what I said, that carbon-12 and carbon-13 are stable and they don't decay. So you can still have the element of carbon in fossils older than 50,000 years old, but not actually have any of that carbon-14, which is unstable to date the fossil with. So that's how you can still find carbon in these fossils that are older than 50,000. All right, what about this whole heat problem that comes up a lot with young Earth creationists and the argument between young Earth and old Earth? And I do think that I might have mentioned this enough that you probably don't need me to come back to this one, but I'm going to come back to it anyway, just in case you didn't pick up on it. But remember what we talked about in the context of radiometric dating, that as these isotopes are decaying, they are putting out radioactive energy. They're putting out heat. So if it's released in varying degrees of, now, while each isotope is released in varying degrees of speed, so sometimes that's going to be thousands of years, sometimes it's going to be millions, sometimes billions. And so for the process to happen that slow, it doesn't really cause issues. But if all of that energy that was to be released in the speed of 6,000 years. Or like I think one of the young earth creationists said that like the year of the flood. So the whole time that the earth was covered with water, a lot of that explains what they're testing in these rock layers. That would have caused the earth to burn up. And I have not seen a good argument against that. And it, to me, it makes sense. I think it's common sense. So that's the heat problem. All right. So do scientists date only with methods based on preconceptions of assumed dates? So this is where we're talking about using those methods. Like if they say, oh, well, we know it's going to be billions of years. Does that mean that then that they're only going to date with methods that can date billions of years? So kind of yes and kind of no. So as mentioned earlier, if they date with a method that isn't suitable, the results are going to be unreliable. But as part of cross-checking, they do try different methods to see if they can find a result that is repeated through the multiple methods. And so they are going to try to use different methods. And so they kind of do use some methods based on that preconception, but they're also using other methods. All right, what about trees standing up, straight up through layers like this picture? Now, geologists call this upright fossils. Young Earth creationists call this polystrate. I don't know why they have two different names. I don't know why the young Earth creationists didn't just call it upright fossils, because that's it's actually much more descriptive, it seems like. But looking at these, they don't actually seem to be like full on trees, but more like tall tree stump. So that's kind of interesting. There have been a lot of them found. And according to the Kentucky Geological Survey, they've even found a whole forest of these things. And so I'm going to be honest, I found so much differing info on these. I do want to come back to it because I want to delve deeper into it. It is very interesting, no matter what your viewpoint is on it. I find that it is kind of an interesting thing. And so we'll discuss these in a later video. So I'm sorry to kind of leave you hanging on that one. But we'll make that into a later video. I just couldn't really find super solid. I would find one answer, but then I was trying to look for something else to back that answer up, and I just couldn't find. You know what? Honestly, if you are watching this and you have better information for me, please send it to me in the comments. That would help me out a lot, because every time I would try to look up a news source to back the source I just read, I would get a different answer, and I was just like, all right, we're just gonna have to come back to this one. So we'll do that. All right. So our last discussion question, last issue question is, what about 50-year-old plains that were found deep in ice layers, if we're using ice layers to date, to create ages of the Earth? So this story actually is in regards to, there was 8 World War II planes in 1942. They had to make an emergency landing in Greenland. And so these planes were then abandoned because, the pilots got rescued. And then they were later recovered, like decades later. But when they were recovered, they were found under almost 300 feet of this snow and ice, but also 2 kilometers away from where they had landed, because what happened is they landed on an active glacier, and on this active glacier, there's also rapid snow accumulation. So when we're talking about ice cores, remember when we were talking about that, I said they don't take them from areas that are prone to this glacial flow, and instead from the interior areas that are stable. Well, these plains are absolute proof of why they don't do that. Because when there is glacial flow, that movement distorts and creates more ice accumulation. So just like many of these methods, of course, there are situations where they can be unreliable, and researchers do their best to account for situations that may not make their findings reliable. And they try to account for those. They try to account for the limitations, and they try to cross-check and all that sort of stuff. All right. So we've talked about the questions, we talked about the methods, we went back to the questions. And so now I just kind of want to give you some of my sort of own personal thoughts on a lot of this. So yes, each of these methods have their issues, and there could be multiple answers to some of these questions. But I do think that they show the value of cross-checking and duplicating dating methods. Cross-dating will help us eliminate problems with anomalies or contamination. And keep in mind, like, rare things can occur that cause issues and can alter readings. I think that's a fair argument. But when you have multiple rocks, organisms, etc., that are dated with these different techniques, and they all line up with the same basic dates in a layer, it does gain validity, and it becomes more likely, and it becomes that other thing is the exception and not the rule, which is what we really have to go by that, So often critiques of these methods will cite problems with them. But what's interesting to me is they don't really look at the fact that researchers actually do accommodate and take those problems into account. And this is why you should always read the methods and discussion when you're reading a paper to see if they accounted for those. Or heck, when you're listening to a podcaster, when they're talking about something, I think it's honest and transparent if they'll say, it could be this. Did we look at it this way? Did we look at it that way? Yeah, actually, we did, and we still came up with this. Or actually, we took that into account. We determined that would be a very, very rare circumstance. So this is the main way this could have happened. There's always going to be something in there that could have made something different. There's always going to be exceptions to the rules. But look for those studies that put that out there and look at it and see, oh, wait, they actually took a look at that, And remember that radiometric dating gets cross-checked with non-radiometric dating, like dendrochronology, when that's possible. And keep in mind that even though dendrochronology doesn't go nearly as deep as some of these others, it still can let you know that at that beginning time, it is staying on track with this time frame. And then it will do it with other types of radiometric dating when another method is not possible. So yes, assumptions of uniformity are made, and maybe, one day there will be proof of activities on the Earth that would have sped up or changed those rates to prove that these dates are far off. But currently the arguments for that would have caused the Earth to burn up. So that would be great if they did. As a Christian, I am always open to saying that God is the God of miracles and could have created all that we see on the earth and not had any issue with the heat problem. But as it appears in our fossil record and our geological record, without even looking at some of these absolute dating methods, I believe he's showing us that the 6 days were not literal 6 days. He was just showing us that he did this. And I'm going to talk about, a friend sent me a video the other day that I thought was really interesting. And as I've thought about it more, it's actually been on my mind a lot because I was working on this at the time and they sent that. And it talked about how this idea that God made Adam as an adult, I think it's a chicken and the egg kind of situation, but he made Adam as a full-grown adult. And so they were talking about, well, then why couldn't God have made the earth as a full-on with all of this geological record into it, like already like this aged earth, right? And I thought that was a neat point to consider. As I've considered it, though, I'll be honest, I don't know why then he would have put fossils into some of those layers. And so that part confuses me. Or when you're even talking about the polarity of the earth, like why would we see those changes through the layers? Like what would his point be of putting that type of stuff in? And so again, God is the God of miracles. He absolutely 100 could have done that. It doesn't make sense to me, and I believe God gave us common sense. I believe that was one of the gifts he gave us as well. And so I do firmly believe that the earth and all the life on it was created by him. And it's amazing and it is wondrous. And regardless of the time frame, it doesn't take away from the miracle of him creating it. It still is an amazing creation. It just may have taken 4.6 billion years, or maybe one day we'll find out that it took 6 billion years and 1 billion was each day. Even though I don't think it fits snugly into a perfect time frame. But I mean, my point to that is just saying it is still an amazing, incredible thing and shows God's enormous power and wonder. And I believe that's what he was trying to show us in Genesis. So as we discussed, there are a lot of controversies and discussions over these different dating methods. Understandably so. They almost all have some flaws in how they date or how they are used. And your level of confidence you put in them, though, can depend on your particular bias. So if you're unsure of what bias is in scientific studies or wonder how to recognize it in others, check out my video on bias here. If this is your first time to hear that there are differing views about the age of the earth among those of faith, check out my video about the different types of creationists here. And I hope you enjoyed this. I really enjoyed delving deep into this. I know I could have gone a lot deeper, but like I said, it was beyond my pay grade. But I loved learning about it. I hope you've learning about it. And I'm excited to see you guys again and talk to you guys again. And yeah, let me know below what you want to talk about next. I'm actually thinking that my next one's going to be about the out of Africa hypotheses and the different out of Africa migration routes that are believed to have taken place. And then I want to talk about all the different Homo species that we see. I hope that's exciting to you, and you'll tune in next time. All right. You guys have a great day. I will talk to you later. Bye.